I'm Yiannis Papadopoulos. I'm a professor of computer science at the University of Hull, and I lead a group on dependable intelligence systems. And today I will talk about safety of AI systems with executable causal models and statistical data science. Mostly, apart from scoping the problem, I will talk about the work of my group in this area. And the work, as you will see, it has two aspects. So on one hand, we develop models by analyzing systems, and in some incarnations of the research, these models are executable at runtime. And on the other hand, we use statistical techniques to deal with some problems of AI which cannot be solved by models. So let me take you back to 90 AD when I start discussing this, when St. John writes the Book of the Apocalypse or Book of Revelation in a cave in the beautiful island of Patmos. And I mention this because many see AI as apocalyptic. Now, apocalypse means revelation, strictly speaking, but it has developed these connotations of dystopian meaning precisely because of this book of St. John. And why? Because in the book, the opening of the four seals of a divine scroll releases the four horsemen of the apocalypse, bringing conquest, civil war, famine, and death upon earth. So enjoy the picture. It's a very nice place to visit in the summer. And after this small touristic kind of intervention, I'm going to move into the talk. Today, AI is seen by many as an existential risk. And this is why I made this apocalyptic reference. So Nick Bostrom, I don't know if you know him. He used to be until recently a professor in Oxford, has developed a very nice metaphor about this. He has pictured the history of human creativity as one of extracting balls, these are the technologies that we developed, from a giant urn, a giant pot. We take these balls out and we do this blindly, okay? So we don't know what will come out, and we cannot put the ball back in. So we have taken out in our history the fire, the wheel, democracy, logic in antiquity. These are also technologies. The gear, the mechanical clock, the free market economy, the public limited company, the car, the aircraft, the mobile phone, the computer. Most of these technologies, of course, we know they are very useful. However, one of them could be malignant, one of these balls, and could devastate humanity. And the problem, as I said, is that we cannot put the ball back in once it is out. So, for example, we took out nuclear power, and we were lucky because we didn't know at the time whether in the future one could bake a nuclear reaction into a microwave oven, because if that was possible, we wouldn't exist. So the question today is, could AI be this malignant ball that will destroy humanity? Can we have some form of super intelligence that will take over the planet, rogue AI or robots, and marginalize humanity? Some people say in 50 years, some people say no, it's still far away. However, whatever the case, today there is a grand technology challenge towards dependable AI and intelligent systems, and the implications for industry and society are enormous. We know that because we have soon autonomous cars coming on the street. We will have swarms of drones doing logistics and delivering goods in your houses. And we will have robots in hospitals taking care of patients, or robots in homes taking care of old people. And we need to make sure that these things are safe. So, which brings me to the work of my group, the Dependable Intelligence Systems group at the University of Hull. We do world-class research on complex software and systems, including intelligence systems targeting dependability as a property, including dependability of AI, for many years now. And we have pioneered some novel techniques for which we are quite well known. And but not only methods, we also develop state-of-the-art tools that have both academic and commercial impact. So some of the tools that we develop are commercial. The work that we do, I think it's, at least in some of the fields of safety or model-based safety assessment is very well known. And in the UK, our research impact is officially ranked as internationally excellent. Every 7 years, we do exercises called Research Excellence Framework in the UK, nationwide. And our submissions are in the public domain. So if you clicked, I'm not going to do it now, on one of those links, you can find it by Googling, I guess. You will see our submission and you will see the impact of our work in this area. So let me briefly talk about the context and motivation of our research before I start to sketch what we do. And I will give you an overview of all the techniques that we develop here. So dependability, we look at dependability, and this is an umbrella term that includes many properties which are of interest, like safety, reliability, availability, maintainability, data integrity, security, privacy. We are concerned about all these properties when we develop systems, of course. And we know that there are increasing concerns about the dependability of new systems, which brings me to what I call the 4 horsemen of the apocalypse, the technological apocalypse. So complexity, intelligence, autonomy, and the openness of systems like autonomous cars, for example. Now, you can see that the 4 challenges form the convenient acronym CIAO, which means hi in Italian. And let me briefly say something about this. So complexity, systems become very complex. You have complex architectures, partly on the edge, partly on the cloud. You have lots of software. So you have modern cars can have 100 million lines of code. How do you deal with this, with the safety of these systems? Intelligence, it's even a bigger challenge. Why? Because intelligence systems are not designed, are not programmed. The behavior of these systems is learned by data. And this is a significant departure from what we were doing in the past. When we were analyzing things for safety, we had a design, we had some code to analyze. We don't now with intelligence systems. And then you have autonomous systems which have no users. And when autonomy fails, because it can fail, there's no one there to take over. And you have these open systems of systems like autonomous cars or multi-robot systems, which are highly unpredictable. You cannot analyze every possible configuration of these systems a priori in design time. So to some extent, safety must be resolved also at runtime. So this challenge, perhaps most people would agree today that it is very significant and it affects many emerging systems, including multi-robot systems, cooperative swarms, machine learning in transport, health, manufacturing, etc. It is an important problem. So what do? We develop a few techniques here to try and investigate and partly address some of these challenges. It's all work in progress, of course. I'm not going to claim today that we solve all, these problems. I don't think anyone has the solution, but I think there's some interesting work here. So for complexity, we develop hip hops and dymodia, which are model-based methods and tools for automating dependability analysis and design of systems. And I will say something about this today. For intelligence, we develop a set of statistical techniques, SafeML, SMILE, SafeLLM. SafeML provides a dynamic estimation of confidence on the accuracy of machine learning. SMILE is looking at explainability of machine learning. And SafeML is looking at detection of hallucination and filtering of unsafe responses of LLMs, large language models. And finally, for autonomy and openness, we develop something called EDDIs, Executable Digital Dependability Identities. These are executable model-based safety monitors for runtime, safety assurance, and adaptation of systems. So for things like autonomous cars and swarms of drones and multi-robot systems to try and resolve safety at runtime. So I will say some things about these topics here to give you the scope of the work. So let me start with the challenge of intelligence, of complexity. And what you see here is a steer-by-wire system that from Volvo, this is. I once analyzed that in a case study that I done together with Volvo. So, and using some tools that we developed in the university. So one of the problems that an analyst will be called to address here is, what if a component fault develops here in one part of the system? What will be the effect on the outputs on the steering actuator? Will I lose steering? Will I have incorrect steering? And faults can be all sorts here. You can have a hardware fault, a software fault, you can have a security breach, you can have incorrect reasoning of a machine learning component if you have one. So it's okay if you have a few faults. However, what if you have 1,000 faults here and you want to examine the effect of combinations of two? You have 499,500 combinations of two. Okay, so around 500,000 combinations of two faults that you need to analyze. It's impossible to do that exhaustively manually or even with simulation, especially if you have a more complex system. And you need some automation here, some effective automation. So for many years, we have been developing a model-based method and tools that simplify this kind of dependability analysis, causal analysis, cause and effect, and the optimization of dependable systems by partly automating the process. And the method is known as hierarchically performed hazard origin and propagation studies, or HIP-HOPS. And I will say a few things about the method. So over the years, it has developed quite a bit, and it supports now a mode of design that spans the life cycle of systems engineering. So we support a safety-driven mode of design in which safety requirements that we capture through a process of risk analysis early in the design can be allocated to subsystems and components during the refinement of an architecture. We support bottom-up safety and reliability analysis of detailed designs to verify that these requirements have been met. And when the requirements have not been met, we can initiate automatic optimization using meta-heuristics of system architectures and maintenance with respect to safety, reliability, cost, etc. And we have developed some methods to produce certification artifacts like safety cases, and to make these models that we create here executable for operational safety monitoring. So let me briefly say a few things about the method. In HIP-HOPS, the analysis of a system are performed on a model of the system, which can be hierarchical here to manage complexity. So you have systems, subsystems, components. In recent versions, we have introduced here state machines as well to describe behavior. And the first thing you do is you specify some local failure logic for the components in this model. So here you specify how output failures are caused by internal failures and input failures. And once you have put this local failure logic, you can execute algorithms to automatically construct a set of fault trees for the system which show how component failures logically combine and propagate to cause system failures. So here you have the loss of steering, the incorrect steering, and here you have component failures, and you can establish the causal link here using this model. So you can do logical and probabilistic analysis of this graph here, and you can establish the reliability and safety of your system. You can also take this graph of causes and effects, and you can simplify it. You can remove the intermediate logic, and you can reduce it into a failure modes and effects analysis table, which shows direct relationships between component and system failures. So this table for each component, A, B, C, and for each failure mode of each component, it will give you if there are any effects on the system, and one or more, and whether these effects are by the failure mode itself or in conjunction with other failure modes. So it will give you a simplified view of how the system can fail. Now, we developed a tool to do all this work, and one question that we asked is, what if a design is found by the tool not safe enough? How can we improve it? Now, design, you can scrap a design, but there are often simpler solutions that you can take. So you can substitute a component, a sensor, let's say, with a more expensive and more reliable sensor. You can substitute a subsystem architecture with one that is better designed. Maybe it has more fault tolerance. You can replicate components, so when one fails, another one takes over. You can introduce voters, and patterns of fault tolerance. You can increase the frequency of maintenance. But here, the problem is that you can have too many options. And the question is design options. And the question is which solution is safe enough, but also cost optimal. And here we are faced with a set of hard design optimization problems that can only be addressed effectively with automation. To give you an example, imagine that you have a system with 100 components, and for each component, you have two options. Let's say a sensor can be from Bosch or from Siemens, and it has different failure and cost characteristics. Now, for 100 components with two options each, you have 2 to the power of 100 possible combinations of different systems configurations that you can make. That's a very large number, 2 to the power of 100. It's 10 to the power of 30 something. Okay, so which solution is optimal when you have these kind of options? So we have developed some algorithms in our tool to do this kind of search and design optimization to find these optimal solutions. So we start again from a model, and this model now is variable, is not fixed. That's the difference now. So these components can have options. So a sensor can be from Bosch or from Siemens, and a large box like this could be an architecture for the braking or the steering subsystem implemented with variant A or variant B by another designer. You can put cost, weight, failure data here, maintenance options perhaps, and then you will give it to hip hops, which will apply an evolutionary design optimization process. So effectively what you do here is you create a design space to be explored, and hip hops will explore it using genetic algorithms or other meta-heuristics. So what it will do here, hip hops, is resolve the variability of this model. So create fixed variants of the candidate design. It will create a population, initially arbitrarily resolving the variability. And then it will evaluate each individual, its potential car in the population for the parameters of the optimization, which could be cost, weight, and dependability. And crucially, we can evaluate dependability here because we can automatically reconstruct fault trees for each variant. So once we do the analysis, we then rank the individuals of the population. We create Pareto fronts or Pareto surfaces or Pareto hypersurfaces. We select the best designs, we breed between them, and we create a new population of candidate designs, which we subject to the same optimization process. And after many generations, we can arrive at a set of optimal or near optimal models, which give improved or optimal trade-offs between the parameters of the optimization. We know that this works. We have applied it to benchmark examples, and we have applied it to, we have incorporated actually in a commercial tool. So it is possible to do this kind of constraint optimization and evolution using these techniques. So other things that hip hops can do is allocation of requirements. So you can do cost optimal, automatic allocation of system requirements, which are captured by a process of risk analysis, examining the system as a black box. So this could be a car, and these functions could be braking or steering, and you can do a risk analysis and find the failure modes and what kind of requirements are imposing, if they are critical, on those functions. And you start from these safety requirements for the system, and as you develop architecture of subsystems, you can allocate them to the subsystems. So this architecture then delivers these safety requirements. And similarly, you can allocate the subsystem requirements to component safety, integrity requirements. So these integrity requirements of the subsystems are allocated to the components. And all this is done in a way that when you put this system in place, the safety requirements at the top are being met. Now, this is an optimization problem. We solve it by using model-based safety analysis and using AI meta-heuristics like genetic algorithms. And on one hand, you need to satisfy safety here, but also you need to do it cost optimally. Why cost optimally? Cost optimality is important here. You don't want to be allocating the highest safety requirements to components and subsystems that include thousands of lines of code, because it's very expensive to develop one line of code at safety integrity level 4, the highest. It could cost you thousands of euros to do that per line of code. So we have developed here technology that can solve this, do this allocation, respecting, taking into account the assumptions that you have made about how each component either propagates or mitigates failures as well, because this defines how the requirements are allocated, whether they can be split, what component will inherit the highest requirement. So we have, in the context of this work, developed a meta-heuristic, which was actually quite fun and received a lot of publicity. A new meta-heuristic which tries to model the social intelligence of penguins. It's effectively a variant of particle swarm optimization, this one, which captures some of the behavior of a penguin colony. Now, penguins are quite good at fishing, and the reason for that is that they have social intelligence, they cooperate. So they work in groups and they collaborate within the group, but they also collaborate across groups by exchanging vocalizations. So if you let a group of penguins out in the sea, you will see that the distribution of penguins will gradually match the distribution of fish in the sea, which makes the colony very effective in fishing, so they can get the maximum catch by spending the least amount of energy, which enables the colony to grow. So we have captured this behavior and in an algorithm, and we have used it to solve this requirement allocation problem, which captured the imagination of the media here. And we have a number of articles that have been published here in this area. The most recent development here in the area of this model-based safety analysis and hip hops is a tool called Andromeda. It's an experimental tool that we have developed that can create safety cases for certification by exploiting the models and analysis that we create automatically with hip hops. So we rationalize the problem of certification. That's what we try to do here. So the safety cases, all of them have the same pattern of reasoning. And effectively, they argue that the system can meet its safety requirements as a whole, the system, let's say a car or an aircraft, which are derived through an exhaustive risk analysis, because the subsystems meet their correctly allocated integrity requirements. And we can prove that the allocation is correct from the algorithms that we have applied, and that all the model assumptions that underpin this allocation are met. Because when you do hip hops, you put assumptions here. You may assume, for example, that for this component to fail, both these must fail independently, and you have to provide evidence that this is the case. And this is true, that the subsystems meet their integrity requirements because the components meet their integrity requirements, and all the model assumptions are met at this level as well. And there is evidence for the above in the algorithms, the fault trees, the FMEAs, and everything that we create with hip hops. And all this is formed into a safety case argument, which looks similar for different types of systems. So it's a kind of pattern. So now, what is important here is that I think for many people is that this tool is also commercial. So we have developed a commercial version that we commercialize, and there are various incarnations of this tool. So we have hip hops by the University of Hull. These are all links you can click, and you can find these tools in the websites, the corresponding websites. You can download an evaluation version from here. You can play with it if you like. There is a version that we commercialize with a company in Germany, ESI. The company is based in Dresden, and it commercializes hip hops in conjunction with their own tool. There's a version with a company in Finland, and we develop a new tool called Dymodia that enables dynamic dependability analysis using state machines as well as architectural models to create state-sensitive fault trees. It's some new work that we do. It's not commercial, this thing, yet. So the important thing about this aspect of the work that we do is that we have achieved technology transfer that has global reach. So our clients include Honda and Toyota, let's say, if we start from the east, and Huawei in China, to Honeywell in the US, Honeywell Aerospace, and from Volvo in the north, then through Continental and Fiat in Central Europe to Embraer in Brazil. So we do have many clients around the globe. Now, I talked a little bit about how we deal with the challenge of complexity. Now, if I return to Chiao here and take the challenge of intelligence, which I think it's an even more important challenge today. And as I said, the problem with intelligent components is that we don't have design artifacts to analyze. You see, in hip hops, I was analyzing models of systems, and here we don't have design artifacts. So how do we deal with this problem? Machine learning classifiers, for example, are often trained to detect objects like traffic signs or pedestrians in the street, or events, process failures, for example, from a time series of data, okay? And they learn how to do this task by being exposed to large volumes of data, of usually labeled data, and these are used to train the classifier to do a specific thing. But the problem here is that these systems learn by induction, learn by experience. So what they learn is a function of the data that they have seen. And they have not seen the whole data that defines the task. So when they operate outside what they have seen, they can fail to reason correctly. And that is a problem. And that is inevitable because induction epistemologically is imperfect way of learning. And it is by definition prone to failure. So there's a fundamental problem here. What do we do? So you can train a machine learning algorithm and you can validate when you train it, its accuracy. Okay, you can use, for example, a labeled data set, 80% for training, 20% for validation. You can calculate an accuracy, but this accuracy will only be a function of the training data set and may drift for data outside this set. So you can see that here. Imagine that you train the algorithm using data that has this distribution, and then you test, you validate using data that has this distribution, which is similar to that, and you get a 93% accuracy on the task. And then you release the algorithm to work on unseen data. And if this unseen data, the runtime data, has this kind of statistical distribution, let's say, then, which is very similar to the training data, you get good accuracy. You can even get higher accuracy. But what if the data, the unseen data, the runtime data, has this kind of statistical distribution, which is different from that? Then you expect this accuracy to fall, and it will fall. And that is a problem. Now, what we have been doing recently, the last few years in the University of Hull, is to develop something called SafeML, Safety of Machine Learning. This is a method that uses statistical techniques, specifically empirical cumulative distribution function-based distance measures, to measure precisely the drift in between training data and runtime data, input data, linked to its reasoning outcome of a machine learning algorithm, for example, to its classification, it does. So we measure the drift, and from that, we can establish a measure of confidence in the accuracy of the machine learning reasoning. So the higher the drift, the lower the confidence that we return in the accuracy of the machine learning algorithm. So that is the key idea behind SafeML. And let me give you an example of application here. Imagine that you have trained a machine learning algorithm to detect lung cancer, to do lung cancer diagnosis, in other words. And you have done that by exposing the algorithm to common symptoms of the disease. So you have trained it with lots of images that have common symptoms of the disease. And then during runtime, during operation, the algorithm is being given images that have rare disease symptoms, rare. Now, in those circumstances, the algorithm operates outside its distribution, and therefore it could be misled. It could be wrong. So, for example, it can fail to diagnose this cancer. And that, of course, could be catastrophic because the patient will not know that they have cancer. But if you put SafeML as a filter on top of the algorithm, SafeML should be able to detect the drift between these and these images, the statistical difference between these and these images. And it will know that it has not been trained, the algorithm, on these kind of images. And therefore, it will lower confidence on the reasoning. It will effectively tell you, do not trust the outcome of the machine learning. We cannot trust that this is not cancer or what this is cancer. And give the image to a consultant to comment on it. So this is what it will do. Now, we have published a couple of few papers on this, and this is cited in the new German industry standard for machine learning uncertainty quantification that was published, I think, earlier this year. So that's quite important for us. We also have done, we've got some awards and some distinctions about this work. I think various people who work in this. So Kuniko Paxton, for example, is one of our PhD students who have received an Alan Turing Institute Award for her work on safe cancer detection. She's looking at a particular aspect of fairness that has to do with the skin color. But she's using statistical techniques to do that and SafeML. And another thing that we develop in this area using similar techniques is called SMILE, Statistical Model Agnostic Interpretability with Local Explanations. And SMILE looks at explainability. So SMILE will try to explain why a machine learning classifier reached the decision it did. So, for example, why it has classified something into class 1 and not class X, why it has classified something as a pedestrian as opposed to a cat or empty space, etc. And it will do that by using statistical distance measures and measuring effectively the statistical distance between features on the examined artifact, okay, and compare this, statistical distance between the features of the examined artifacts compared to the corresponding features of the data in the training data set. Okay, so we will measure the distance between the feature of the examined artifact and the distribution of features in the training data set. And by doing that for each feature, we can establish a measure of how much similarity and how much dissimilarity exists, and therefore why something is classed as 1 because there's more similarity and not as X because there's more dissimilarity. This is the idea. Finally, we developed something called safe large language models, which apply statistical techniques to do things like hallucination detection and distinguish between safe and unsafe responses of a large language model. And what we have done here, we have done a case study on wind turbine maintenance together with Électricité de France. So we took a an open source LLM, Llama 2, and we trained it to do specifically engineering maintenance using a knowledge graph that shows relationships between alarms, so series of alarms, and maintenance actions. So in this way, we have created a specialized version of this, and we created a conversational agent that can work with maintenance personnel to try and generate engineering maintenance advice in the output. And now what we have done here to make this safer is we take this output, and the first thing we try to do is hallucination detection. How do we do that? We generate multiple instances of the output for the same prompt given, and then we do pairwise comparisons here of the distance between the outputs. Of course, the outputs have been encoded so that you can measure in vectors, so that you can measure the distance. And by doing that, we are able to detect inconsistencies between the outputs on the same prompt. And from those inconsistencies, we can suspect hallucination. And the other thing that we do is we take the output and we compare it to a dictionary of unsafe outputs. And if the output has similarity to this dictionary of unsafe outputs, then we can also suspect the output as being unsafe. And we can provide the output to the maintenance personnel and ask them if it is indeed unsafe. So we have human in the loop. And if it is, we extend the dictionary. Now, this is our most recent work in this area. There is a paper on that. I will give you some links to the papers. Now, what is important, I think, to say at this point is these things are work in progress. I'm not going to claim here that we have solved the problem of intelligence. No, we haven't. Okay, we are doing research and we are doing some interesting things, and these things have their limitations, but we try to improve a situation which at the moment is very problematic in this area of safety of intelligence. So let me briefly say a few things about the challenge of autonomy and openness. So autonomy, there are no operators when autonomy fails to take over. That's a problem. Openness, you have infinite configuration in a system of a multi-robot system in a factory or autonomous cars connected to traffic lights, etc., and infrastructure. You cannot analyze all those configurations of this system at design time. It's impossible. You can have emergent behaviors and uncertainties. You can have higher security threats in systems of systems. And these systems are hierarchies of equals. There's no hierarchy of control. So safety is a big problem because there's no boss in a system of autonomous cars that can control safety. So the implication is at least part of dependability assessment and certification and assurance need to be moved at runtime. So we need to move from the old model of doing safety at design time. Now we have been developing a concept of executable digital dependability identities, which are modular, composable, and executable specifications of dependability for components and systems in open systems of systems. So these are models which are executable. And these models are derived from safety assessments, the ones that we work with. So they can be Bayesian nets, fault trees, Markov models, hierarchical state machines, state-sensitive fault trees, conditional safety certificates. So we have been experimenting with various models. And we developed this in a European project called Sesame. It's just concluded, actually, with the results. And we have developed something called the Open Dependability Exchange, in which we can encode these kind of models and then make them executable because we have algorithms to make them executable. So let me give you an idea of how this thing works, the EDDI. So here you can see the architecture of an EDDI. So there is an event monitor which monitors the system and try to detect significant events, faults, for example. And we have developed a little language here that can do long-term temporal monitoring to detect events. It can instantiate, for example, in runtime, circular buffers to do the long-term monitoring. It can do differentiation, integration, etc. There are various operators to detect significant events. Some of them are unambiguous, but some events may require further diagnosis to find what's the underlying cause. And we can pass this to a diagnostic engine that could use selectively traverse the branches of a fault tree or use other means to do the diagnosis of causes. And then the events that we detected and diagnosed causes, once they are unambiguous, they are passed to high-level reasoning applications that execute these high-level models, Markov, Bayesian nets, hierarchical state machines. And this execution will be able to produce effects, possible effects, to project risk in the future, to generate alarms, diagnostics, effects of failure, guidance of corrective measures, perhaps. Now, the important thing about this system here is that it is not isolated to one system. It works on a system of systems. It communicates, in other words, using protocols with other EDDIs of other systems in the system of systems. So, for example, we can ask guarantees from other systems to meet demands in some of these models to make sure that we are safe. So you can see that here. You can see a system of systems, a multi-robot system. So you have a number of systems. And you can see the EDDIs of these systems. They are sitting on each system. They are executed, the models, and then they communicate between them in order to resolve safety. So they can exchange guarantees and demands and data in order to guarantee safety. And we have done experiments with security in this European project as well. So we try to inject failures and see how it responds, the thing, because the failures are modeled in there. Now, the most recent development on this, and I'm close to the end. I took a lot of time. We are the most recent development on this is we develop a version of the EDDI as a Bayesian net, a probabilistic model to calculate potential risk, etc., and do diagnosis and prognosis in a collaborative fashion, but which exploits belief values returned by SafeML. If you remember, with SafeML, we can give a kind of probability that a machine learning algorithm is wrong, has failed. So in that way, we integrate the failure of intelligent components into a probabilistic framework that includes other failures in a system of systems. So that's very recent work. We haven't even published the paper, but this is what we do now. And the applications are from factory automation to drones that do maintenance on electrical infrastructure and drones that do disinfection on hospitals in this European project that I mentioned. So there's other related work, of course. We are not the only ones to develop stuff to address these problems. So I put some names here. I'm not going to discuss them, just for your interest. And there's much more, of course, that I haven't mentioned here. Now, I would like to close with a couple of reflections in all this. So here, I'm sure you have seen Sagrada Familia somewhere, if not in person, a beautiful cathedral designed by a genius architect, Antonio Gaudí, using intelligent design. And this thing, surprisingly looking in shape similar to the Sagrada Familia, is a termite mound. So this was built by millions of termite ants without any design. And I think that one possible future of technology is that we will move from intelligent design to things that learn, to things that they evolve, to things that they are loosely collaborating, etc., like the ants. And we don't want to move from something like that to something like that. Okay, so the move is both exciting, but it is also problematic. Which brings me back to my initial slides when I said, is AI a risk, an existential threat? So let me close by looking at AI as Pandora's box. Perhaps you know the ancient Greek myth of Pandora. Pandora opens a box gifted to her by the gods, and when she does so, all the evils that we have in the world escape, including war, death, etc., illness. But she's quick enough to close the box in time to keep hope inside. So we open the box of AI, and I think what we need to do, we need I think we cannot close it. We cannot put AI back into the box. It's impossible. We have to go through the portal of AI somehow, and we have to go without destroying the planet and humanity, etc. So we need much more work and investment in the area of safe AI to try and achieve that. So I put here a few papers. So there are lots of papers on hip hops and model-based safety assessment, which might be useful even when you just, a system will not only have AI, it will have AI as part of something bigger. So you will always need also a kind of neurosymbolic model to address safety. So a most recent paper, which was just published, is this on hip hops. I put a paper on SafeML, a paper on Smile, and a paper on Safe LLM. Again, all these are quite recent papers. And I put a paper on EDDIs. So you're welcome to have a look at these papers if you haven't already, and to come in contact with us and discuss all this stuff. And we will very much welcome questions and comments and post-talk communications and possibilities of collaborations, etc. All these things are very welcome.